Hello, sir. You are live now. Please start.
Okay. Just give me a second. Hello everyone. In the live session for the course called Behavioral Theory of Systems with a view towards data-driven control. I have a couple of offline questions. Try to answer them first. Then meantime, there are live questions. We'll answer them. Yeah, the first offline question that I have with me is, what are some examples of persistently exciting input functions? Well, if you want persistently exciting input functions, there are quite a few. You can just persistently exciting also requires so persistently exciting functions. Also, if you look at the idea of persistently exciting carefully, you'll find that there is this okay. The order is also important. I mean, persistently exciting of what order? So if you want, you can create such input functions, right? And just look at the Hankel matrix, the corresponding Hankel matrix, and try to find out that this guy is full row rank or not. Yeah, that's persistently exciting for you. You can create all sorts of functions. Like for example, if you take a random uh, a random process, like a sequence of independent, identically distributed random numbers, yeah, then usually those will turn out to be persistently exciting. But you can create other such things as well. So some common functions that we know, they are not persistently exciting. For example, if you look at, I think the step function, I have to sit and check this carefully. But as far as I can recall, step functions are not persistently exciting. Although it appears from the name, it suggests as if it's going to be persistently exciting, but it is not. So my suggestion is that if you want to learn about, if you want to learn about specific functions which are persistently exciting, what you can do is just look at the definition, create the Hankel matrix and put in these numbers so that this matrix turns out to be full row rank. Then you're done. Okay. How does NPM take into account noise in the data? That's a very good question. NPM actually usually cannot take into account noise. What I mean by that is, if you collect the data, the input output data, right? And from there, you want to create the maximum, the most powerful unfalsified model out of the data that you have collected. Now, suppose that data is corrupted by noise. If the data is indeed corrupted by noise, the NPM will not know that it is noise. It will think as if the input-output relationship is such that the output that I'm getting, the noisy output that I'm getting, that is the real output to that input, right? See, NPM, first of all, doesn't distinguish between input and output. It just says that, these are the trajectories that are admitted by the system. So if the trajectories themselves are corrupted by noise, the NPM process does not know that. So it will think that this is a legitimate trajectory, and it will give you a differential equation, system of differential equations, which will have this guy as a as a legitimate trajectory. So the problem with that is you will end up getting equations which are you'll end up getting a system, an NPM, which actually is quite far from the reality. Yeah, because the data is corrupted by noise, but NPM doesn't know that. It will try very hard to fit into, to give a system which sort of allows this trajectory also within the behavior. In the end, what will happen is it will be too relaxed. It will be too few equations, or equations of equations such that too few restrictions will be there, so that it allows these aberrations to also be normal, right? So that's a problem with NPM. That is why what is often done is, instead of looking at the NPM, one looks at the system which approximately fits in the data. See, this problem of NPM not being able to capture the actual dynamics, not being able to distinguish between the noise and the actual dynamics, is something which is very common in learning parlance, learning literature. It's called overfitting. That's precisely what happens with NPM also. It overfits the data by giving you a very relaxed system. Yeah, that's why what is often done is you take the data, but you know that this is corrupted by noise, though you don't exactly find the NPM, but you get a system which approximately gives the data, approximately houses the data, right? And then this approximation you've done in such a way that it takes into account that there is this noise, and gives you a system which is actually very, very close to the original system. And that's why you do approximate modeling. So NPM is an example of exact modeling, yeah, which cannot cater for the which cannot distinguish between noise and data. So it does a bad job when the data is noisy. So to counter for that, you use approximate modeling. I don't think we did much about approximate modeling in the course, but if I'm not mistaken, I did mention it. I think I did mention it towards the later part of this course. I did mention things like, you look at the Hankel matrix and look at the singular value decomposition of that, and then based on the expected rank of the Hankel matrix, which is different from the exact rank that you are getting, the actual rank that you're getting from the data, because the noise actually has the tendency to increase the rank. So you take the expected rank and you take only that part, do an approximation, what do we call it, do a low rank approximation of the data through SVD, and from there you find out the null space, which gives you the approximate model. That has its own problems though, but that's the rudimentary step that you can take to do approximate modeling to counter for the overfitting problem of MPU. Yeah, I hope that answered your question. Let me see if there are any live questions. No, there aren't any live questions. So these were the two offline questions. There aren't any online questions as of now. I can't see offline questions as of now. So I'm going to mute myself unless there are questions, unless there are online questions. I'm going to mute myself. Okay, I'll come back when there is a live question. Yes, back there is a live question which says that can the methods work for colored noise or changing variance? Uh, the method that we did describe doesn't really need much assumption about the noise, if I remember correctly. What you do there is look at the Hankel matrix, look at the input-output Hankel matrix. You remember that the left kernel of the Hankel matrix is the one that gives us the equations, right? When you look at the left kernel of the Hankel matrix. So, and we know that this the rank of the Hankel matrix, there is this, it's increasing, but it's the difference in ranks, that saturates after some point of time. Yeah, after you have, it depends on the lag of the system. After you have calculated these, after you have increased these matrices, these Hankel matrices, if you after you have reached to a sufficient size of this Hankel matrix, the rank does not, the change in rank as you look at bigger and bigger Hankel matrices, the change in rank saturates. Okay, that's the number of, that's the input cardinality as we discussed. Now the thing is, these numbers get messed up when there is noise. Right now, without making much assumption about the noise, one can just think of the noise as a, so this Hankel matrix, look at the Hankel matrix. See, the Hankel matrix that you have obtained of any particular order, the Hankel matrix that you have obtained, that one is different from the true Hankel matrix, the one that you would have obtained if there were no noise. Yeah, so let me call that H0. Yeah, H superscript 0. Subscript, of course, is the order of the Hankel matrix. So H superscript 0 is the true Hankel matrix of size of order k. So H sub k sub 0, H sub k sub 0 as opposed to H sub k. So H sub k can now be viewed as a perturbation of H sub k sub 0, the true Hankel matrix. Right? So you have the true Hankel matrix and you have the Hankel matrix that you have obtained from the data. So what one does in the approximate modeling is that I ideally should be calculating left kernel of k sub 0. But instead, because I have H sub k only, which is corrupted by noise, if I calculate the left kernel, I'll end up calculating left kernel of HK, which is wrong. And that left kernel will be much smaller because HK rank will be much more than HK 0 rank, right? Because noise adds to the rank, remember? Yeah, because there's no pattern in noise. That's why the noise adds to the rank. The noise is, even though the noise is being generated by a system, still it is being fed by a white Gaussian noise. You see, whenever there is color, whenever there is colored noise, you can, that colored noise actually can be viewed as a white Gaussian noise being passed through a filter, right? So therefore, the noise itself has this, the colored noise itself is noise after all. So that's why, without getting into the details of how the noise was created, without going into the statistics of the noise, it is safe to assume that HK naught perturbation added to it is HK, right? Now, what sort of perturbation do we expect? That depends on the kind of noise that we have, colored noise, this, that, but whatever it is, one can always look at this perturbation, look at this situation from the perturbation point of view, and one can ask the question that, now that I have this HK as opposed to HK naught, I would like to take a guess for HK, right? And what sort of guess I will take? I will take this guess that I know that HK naught rank is smaller than HK. And I have an idea about what that rank would be. I'm taking a guess about, I'm thinking that, okay, I know the rank. This is what the expected rank is. So among all those smaller rank matrices, which could be HK naught, I will take that as the HK naught, which is the least distance away from this guy. That's the least square approximation. Yeah, and that is what we are doing when we are doing approximate modeling. That's why we don't worry about what is the nature of the noise, whether it's a colored noise, whether it's a white Gaussian noise, and so on. I don't worry about that at all. I just assume that the HK that I've obtained is a perturbed version of actual HK naught. So what can HK naught would be? The HK naught that we are going to obtain is, the best possible low rank approximation. That's what is done. Is this flawless? Well, this is not. This has its own problems because this HK naught that I'm getting by doing this low rank approximation may not even turn out to be a Hankel matrix. So do I worry about that? Those are the things that which require further analysis, and we did not discuss that in the course. Those who are interested, they can read up about such things called structured low rank approximation methods for approximate modeling of dynamical systems. Yeah, this was beyond the scope of the course, so that's why we did not cover it. But this is what is done. As I said, this is the rudimentary step that you can take to do approximate modeling. So in a nutshell, the approximate modeling is kind of agnostic to the statistics of the noise. So it doesn't matter what sort of noise we are talking about, whether it's a white noise, whether it's a colored noise, really doesn't matter. Yeah, because after all, we are going to assume that the noisy data is the perturbation of the original data. So what could be the original data, or rather what could be the left kernel of the original data? It is obtained by taking the left kernel of the best possible low rank approximation of the corrupted data matrix. Okay. I hope that answers your question. Your name is Filter 8. I hope I could answer your question, Mr. Filter 8, Mr. or Miss Filter 8. Once again, I'm going to mute myself till I have the next. Thanks, Mr. Gautam Sinha. It turns out Gautam Sinha is Filter 8, I think. Thank you.
Hello, sir. There is a query.
There is an online question. Let me check. Yeah, very nice question. Gautam Sinha, Mr. Gautam Sinha once again has asked, what is the framework of data informativity? Is this something new? Yes. So over the past decade or so, a lot of emphasis is there on coming up with controllers from data directly without going into system identification first. So here's the deal. Can we design a controller which will stabilize the system without doing the system identification first? Just look at the data, and from the data itself, tell me, can I design a controller which will be such that which will do which is such that when I put this controller into the system, I will have stability without uh, any problem. Just give me a second. Sorry. Yeah, there was a visitor here. So where were we? Yes, I was discussing about data informativity. Yeah, like for example, I have this data and I want to have a controller directly from the data. So which when I connect with the system will give me stability. So this approach of designing a controller is the so-called direct approach as opposed to the indirect approach, where you look at the data, do system identification first, and then you do model-based controller design, right? Now, the moment I say controller design, the one that we just mentioned, that is the property of stabilizability, isn't it? Given a system, if you can come up with a controller, feedback controller, which can stabilize the system, that stabilizability. So in a way, we are asking the question of whether the data is stabilizable, whether the system is stabilizable or not. Can this be verified from the data? If I can do that, then I can design a controller as well. Similarly, suppose I want to do LQR control directly from the data. I don't want to go to the system. When can I do that? Now it turns out that if I have a data which is such that I can do the system identification, then of course I can do system identification first, and then I will check for these questions. But sometimes it may so happen that the data that I have may not even be sufficient for full system identification. What if it's not persistently exciting? We don't know in that case whether the data is enough to identify the system uniquely or not. What do we do in that case? That is where the idea of data informativity comes in. Given a property, if the data is such that if the data has a property such that such that suppose system cannot be uniquely identified, but this the data is such that this all possible non-unique solutions that I get if I run a system identification, all those all those distinct systems that I get when I try to identify. See, there is no uniqueness there because the data is not sufficient for unique identification. So I have multiple systems. But the data is such that among all these systems that I have, yeah, which comes out of the system identification algorithm, multiple systems as a family, it turns out that that property is common to all of those guys in the family. Then of course the true one lies within that family because the true one also satisfies the data, right? But in addition to the true one, there are so many other systems also which I have falsely identified. But it turns out that the entire family has that property that I was looking for. In that case, the true one will also have that property. So in that case, that particular data, which is such that all the systems that satisfy that data, yeah, all those unfalsified models are satisfying the data means unfalsified models. So not the unique. There are multiple such unfalsified models. Among those all those unfalsified models, yeah, all of them have that same data, same property. Then for that particular property, this data turns out is called informative. That's the idea of informativity, right? When you apply it to various different situations, you get different ideas of informativity. That is what data informativity is. Yeah, I hope that answers your question. Yes, it is something new that we have not done in the course, but it's kind of the next step. There are nice papers on data informativity already. You can check out those papers, and I'm sure you'll be able to understand what is written there with the background that we have provided through this course. Okay, thank you. Once again, I'm going to mute myself. We have not received any online questions after the last one we answered. I'll get back. Let me mute myself now. I'll get back to you the moment I have another question.
हेलो सर।
हाँ ओंकार जी।
सर शुड वी क्लोज दिस?
हाँ अभी तो और कोई है नहीं, कोई लाइव क्वेश्चन भी नहीं है, हम करते हैं।
ओके सर, थैंक यू।
ठीक है, ठीक। ओके।